That solutions can be real or they could be imaginary, and real ones we'll be able to see on the x-axis, and imaginary ones have what kind of answers?
Imaginary answers.
Yes, imaginary answers. How do we know it's an imaginary number? Right, parabolas won't have an x-intercept, but the answers will have an I in them, right? They'll have an I in them, and we won't be able to see those. All right, we have a little bit of some vocab here. Distinct zeros is if I look at a graph at first glance, I just want to count up how many x-intercepts it has. Okay? That's what they mean by distinct. Even though there might be some solutions that are duplicated, we would just count it as one time. So we just look at the graph, how many times it hits the x-axis. And then multiplicity is when we have an identical solution, like on our warm-up today. Identical solutions. And what that does is it creates it doesn't go all the way through the x-axis. It will bounce. It'll just kiss the x-axis. Okay? Or it could be what's called an inflection point that we'll talk a little bit more about later on. Okay? So, the fundamental theorem of algebra, and you have this already on your sheet, is the degree of a polynomial in one variable is the number of solutions you have to have. And the imaginary solutions always come in pairs. Okay? Conjugate pairs. So here's a couple of examples we're going to go through. You have this graph on your sheet. And I'm telling you that it has a degree of 3. If I just look at it at first glance, tell me how many distinct zeros it has. How many x-intercepts? 3. Just you have 3, okay? So we could, right? 1, 3 has 3 distinct zeros. If it has a degree of 3, how many answers does it have to have? 3. The answers, the solutions, is equal to the degree. Do we see them all? Are they real? Yes, we can see them all. All 3 are accounted for on the graph by those red dots. So how many do you think would be imaginary? 0. If I have to have 3 answers and all 3 are real, no imaginary, so there would be 0. Okay? That's probably like basic. Now we're going to go to level 2. We're leveling up. Okay, you ready? This one has a degree of 6. It's not quite a parabola. It's kind of funky over here on the left, isn't it? Degree of 6. So if I just look at it at first glance, how many times does it touch the x? 2. All right, now, how many solutions is it supposed to have if it's a degree of 6? 6. I should have 6 answers. How many answers can I see on my graph? 2. So 2 of them are real. All right, now, are you ready? This is hard math now. We're supposed to have 6 answers. 2 of them are real. So how many are imaginary?
I don't know. It's really hard.
Start out with 6, right? We can see 2 of them. How many are imaginary? 4. Okay. Okay. Now keep in mind, if you want to double check yourself, the number of reals and the number of imaginaries, if you add them numbers together, you should get your degree, 6. Okay. Multiplicity, it's on your sheet. It should be. Is it not? Right here. It's right there for you. We're going to do one in just a minute. It'll bounce. We're going to do one. All right, let's look at another one. We keep going. All right, let's look at what multiplicity would entail. Okay, now I did this on purpose. I wrote it in factored form. I wrote this in factor form and gave you the graph, okay? If I were to solve this like we did on our warm-up today, you're going to miss multiplicity. Just wait. Can you wait like 5 minutes? I don't want you to miss this. Okay, so if x plus 3 is a factor, what would x have to equal? Negative 3. Whoops. If x plus 3 equals 0, what would x have to equal? On your paper. X minus 2, what would x equal? Okay. All right, so now we did that part. We did that algebra like we did on our warm-up. What do you think the degree of this polynomial is? If I were to multiply all this together, what do you think x to what power would you get? Fourth? X to the fourth? X times x times x times x, x to the fourth. So we're probably looking at a degree of 4. And it does resemble the shapes of the graphs on the back of your paper, right? Looks like that W, as Brendan says. All right, now if I look at that graph, how many x-intercepts does it have? How many times does it touch the x? 3 times, see? So it has 3 distinct zeros. How many solutions can we see on the graph? There's only 3 x-intercepts, right? So I only can really see 3, but this one has a multiplicity. See the bounce? So this counts as 2. See, look at your answers that you got. That's a real number. Negative 3 is a real number. 2 is a real number. And 5 is a real number. So there's actually 4 real ones, even though there's only 3 x-intercepts. This little bounce is showing you your multiplicity. Yes. If it bounces, it counts as an even number. Let me rephrase. Counts as an even number of multiplicity. If it's an inflection point, it's an odd number of multiplicity. It's usually 2. We'll talk about inflection later. Okay. I don't want to get too confused on inflection points. All right, so if we have a degree of 4, and there really are 4 real answers, right, up here that we solved, how many are imaginary? 0. 4 of them are real, right? Do you see any eyes up here?
No.
No. So all 4 are real, and 0 are imaginary, and we have 1 multiplicity. Yes? An I? Oh, good question. How could there be an I? If you had a factor that looked like something like that, then this would give you an I, because x squared plus 4 equals 0. And then if you subtract 4 and taking the square root of that negative, that would give you plus or minus 2i. So that's how you could get those imaginaries to pop out. Yes. And that's actually what we're going to be doing tomorrow. All right? So a little sneak peek of tomorrow. All right, what other questions do you have? That was a good one. Your first